Hey guys, what's up? Eddie Allhole here with KissAnalog.com. Today we're going to jump back into that Tripp-Lite Power Supply schematic, the PR60. That's a beast of a power supply. It's Jerry Motes that brought this up. He was looking for a way to add inrush current protection to his power supply, and I guess he has done that, and it sounds like it's working. I'm curious to know what part he put in there, and also what the current rating is on that fuse that he has in that thing, because it's got to be taking a pretty good size inrush current. He was tripping circuit breakers. That come to anybody's attention that they'd want to do something about that, right? Well, so another good question he had was, why didn't the manufacturer add that in the first place? Well, sometimes bean counters get in the way, right? They just start saving money on every part they can. If you're doing a big power supply like that, they may feel like you're going to be on a big circuit, big branch, and they may not think it's an issue. And adding parts, every part you add, there's a possibility that it could be, something that's going to fail. But at the same time, as a protection device like that also, it's going to protect the parts that are seeing all that inrush current. So I think it's a good idea to use them. Now the parts could be way over designed, so they're very robust. But if they did that and spent all the money to do that, then why wouldn't they do circuit protection as well? So anyway, it's one of those things where you have a budget when you design a product, and it probably just didn't fit the budget. So hey, we're going to jump into the schematic. I'm going to show a simplified schematic here in the notebook. We're going to use the iPad and a drawing package that was suggested by the Fried Meal. Not a particular drawing package, but just a drawing package. And so I found one. Let me know what you think of that, how that works out, if that makes things easier. And then I'd also like to just make a note on Ray Albert's commented, if you guys didn't read that. I misspoke when I was talking about the circuit, and I called these two blocks. I can't find the parts, so I don't know what they are, but I didn't mean to call them bridge rectifiers. They're not full bridge anyway. They're two diodes in the package. So just wanted to shout out and say, hey, thanks for correcting me on that. Don't want to mislead you guys. This video we want to thank David Luther for. He asked about paralleling transistors, and that is a subject that comes up a lot. How do you safely parallel transistors so that you get somewhat equal current sharing? You're not going to get exact current sharing, but at least you don't get thermal runaway, and I think Tripp-Lite did a good job on that, and I'll show you how they did that. So that's what this video is about. So let's just jump into that, okay guys? And by the way, I'm going to do another video on the protection circuits later. Okay, so let's get this video going. Hey, thanks for watching, guys. Alright guys, welcome back to this power supply. This is the Tripp-Lite PR60. So this is a power supply that we started looking at in another video, and it was brought to our attention by Jerry Motes. He was curious about how to protect this circuit for inrush current, because right now there's very little circuitry in the input part of this power supply, and that's all right here. I kind of walked through this power supply in the last video. Now I'm using this drawing package. It was a good idea. Fried Mule suggested it, and I took him up on that suggestion. I think it's a good idea. So basically we have the input circuit right here. This is the primary side of the transformer. That's the input side, and then all this other stuff is the secondary side, okay? Okay, one thing to notice is, you notice that this bank of transistors here, each one of these emitters have a 50 milliohm resistor, a 0.05 ohm resistor, before it gets back to the capacitors right here. See, it has to go through, each emitter has to go through these, right? Now part of trying to understand circuits sometimes is just redrawing it, okay? So let's do that. Alright, so with the circuit redrawn like this, it's a little bit easier to see. If you ignore this for right now, this part's really easy, right? The transformer through the two diodes to the plus side of the caps to the positive terminal, and there's 6 of these 6800 microfarad caps that charges up, and the return side came down. That center tap just came right down to the caps, right? But then where it got a little tricky is where it went through that resistor and then up through the emitter, and then there's 3 of these transistors. So let me say, I should say these transistors like times 3 of them. Okay, so here's the current path. You got this, you go through the load, down to the transistor, to the emitter, to the emitter resistor, and back to the cap, right? That's how we walked through it before. It's a little bit easier to see now. You can see how this control voltage can control this transistor to turn on, right? Now, what is that resistor there for? That's the big thing right there, okay? What that resistor does is offers negative feedback. So when you put a voltage here, let's just say you put 1 volt, okay? Let's just say you put 1 volt right there. If you put 1 volt from here to here, okay, you just put it right up here to this base and then down here to this resistor. So if you just come down here and put this power supply and hook it up there, then you get 1 volt. You get about what? Let's just call it 0.7 volts here, okay? Let's just call it 0.7. Maybe it's 0.6, 0.65, but you know, around 0.7 volts drop from base to emitter. So that leaves 0.3 volts here. Okay, alright, so then there's your 0.7, 0.3. Now you could kind of calculate your current, because you say, well, got 0.3 volts divided by my 0.05 ohms. What is that? That's about 6 amps. That looks like about 6 amps. So that's how you can control how much current goes through this transistor. He can't just run away and have whatever current he wants. Alright, so let's say you have them in parallel. I just showed 2 of them, but you can imagine the third one over here. There's 3 of them. But okay, just 2 of them in parallel. Let's go back to that 1 volt. Let's say you have 1 volt here. Okay, putting it between right here and here, right across here, we got 1 volt. Well, we go back to say we have 0.7 volts here. We're going to say we have 0.7 volts here. But what if this is 0.72 volts? Okay, maybe it's just a little bit different on that transistor. Well, then, you know, you're going to end up with the rest of the voltage here. So you're going to have about 0.3 volts here, and you have about 0.28 volts here. So yeah, you're going to have maybe 6 amps here, and you know, I have to do the math there, but you're going to have a little bit less current. So you might have about 6 amps to this guy, and this one we'll have to do the math. Okay, so we had 0.3 volts. We had the 0.3 volts on the one, and we had 0.05 ohms, and we're going to divide that. So that was at 6 amps. On the other one, let's say if we had 0.28 and we have 0.05 ohms, then we have 5.6. So yeah, maybe it doesn't share perfectly. And also, what if that 0.05 ohm resistor, you know, say it's 1% tolerance, and it's going to, one's up and one's down, so that'll change the current. But the point is, there'll be some tolerance in this current sharing. But here, let me see, I'll just write that down. So I said 6 amps here, I'll just say 5.6 amps here. Okay, so now, you know, we get 5.6 amps here, you know, we add them together, and that's how much current's coming into this node here. And then splits up and comes this way. That's Kirchhoff's current law. Kirchhoff's voltage law says we have 1 volt here. If we make a loop, it has to equal this 1 volt. So 0.7, 0.3, that's equal to 1 volt. We're back to 1 volt, so it had to be equal to this. So we start off with 1 volt, we go in this other loop, 0.72, 0.28, nothing else. So we got to be back to 1. So those two things have to equal a volt. So that's Kirchhoff's voltage loop, or law. All right, well, hey, there's how these things share. This is negative feedback. This guy, as the current goes through, the more and more current goes through here, the more he subtracts from this guy, and the less voltage you have across this guy. The less voltage you have here, the less you're going to be able to turn this transistor on. So that transistor will start to turn off. So then that'll mean it'll kind of self-adjust itself to some point where, you know, you get 6 amps in this case. Now if this thing dropped down to say 0.6 volts, well then you'll get a little bit more current through here. But that resistor, you know, worst case scenario, you can only have 1 volt across it, meaning there'd be nothing here, which that can't be unless the transistor fails. But so the point is this thing can change a little bit, and you'll get a little bit of change here, but each one of these will heat up and change, you know, to a certain degree, and they'll somewhat track each other. But you can see how these resistors offering this negative feedback keep these things from going to thermal runaway. Otherwise, without this transistor, this guy might heat up a little faster than this guy, and he might have a little bit different, you know, they're not exactly, even if you get them out in the same batch, they're not exactly the same. So one of them is going to start off with a little bit more current, and that one will heat up faster and start taking more current, and that's thermal runaway. And these resistors stop that. They force the current sharing. So that's how that works. Alright guys, hey, thanks for the questions, and I think this is a really good topic. Thumbs up if you like that. That helps me. Thanks guys. Okay, so we're paralleling these transistors, right? Well, what are these transistors? Here's a data sheet, 2N3771. It's also good for 3772. It's one of these big old TO3 kind of cans. That's a TO3, big metal can with 2 pins, and those 2 pins, pin 1 and 2 is a basin emitter, and the can itself is the tab, they call it, is a collector. Okay, so yeah, these guys are big boys. Now when you're looking at transistors, one of the big things you're looking at is if you want to have a lot of power, you want to have some massive, you know, you might want some big old massive thing like that to dissipate some heat. But a couple of the other parameters are the voltage, the collector to emitter voltage, 40 volts. So you can't have more than 40 volts on this. You really don't want to do even that much. So, you know, you want to derate this somewhat. Okay, so you don't want to use near 40 volts. 70% derating is probably a good number to use. So, you know, maybe 28 volts. Okay, so the other thing you want to look at is collector current. IC collector current, 30 amps. Wow, 30 amps. Well, this is a 60 amp power supply, so why do we have 6 transistors? Looks like 2 of them will handle it. Well, even 3 if you derate, right? Well, that's not quite true, and I'll show you why. Now, the other thing is base current. You can put 7.5 amps into the base. I mean, that's a pretty beefy transistor. Put that kind of current. So, okay. So now, look at this. 150 watts total power dissipation. So, that sounds pretty good. You can dissipate 150 watts on this guy. Well, how do you dissipate power? Well, when you're putting current through it, and you got a voltage drop on it, current times voltage is power. So let's see how much power we're going to dissipate on this guy. Now if they're fully on and they're not regulating voltage, then that's the best case scenario. But if they're regulating voltage, you're going to have more volts drops across them, right? Because that's how you regulate, is dropping voltage across your transistor. Oh, and that's the other thing I want to point out about this is this 150 watts, that's when the temperature of the case is less than 25 degrees C. That's room temperature or cooler. You can put 150 watts. So that's like an ideal case, right? You'd have to have that heat sunk so well, and you'd have to have like liquid cooling or something to dissipate 150 watts on it, because that's going to get hot. Okay, so this right here, thermal data, resistance from junction to case, that's a very important parameter right there. 1.17 degrees C per watt. So let's say you have 10 watts dissipation across this thing. That will be 11.7 degrees C rise from room temperature. So with just 10 watts, you're already rising above room temperature, you know, 11.7 degrees, almost 12 degrees. So this 30 amps that they're talking about, if you put 30 amps through this thing. Well, here, let's see how we create wattage. What we're looking for here is this VCE SAT. See that guy right there? Collector to emitter saturation voltage. Collector emitter saturation voltage. When you turn it on, when you put a lot of voltage, see here's the voltage on the base emitter. When you put, say it's 2.7 volts, you can get 15 amps through there. So when you start putting voltage on this base emitter, then this voltage collector emitter is going to drop down to close to zero, but not quite zero. It's going to have, it's not ideal. You're going to have, it looks like with 15 amps, you're going to have 2 volts. Now, if you did get 30 amps through it, you'd have a 4 volt drop. So 30 times 4, that's 12, 120 watts right there. So that's your max power right there. But if you did that, if you put 120 watts on this thing, and then you go up here and multiply 120 by that, that's going to be over, you know, that's way over 120 degrees C, right? That's above room temperature. So that's going to be very, very hot. Now here's another important parameter, the DC current gain, okay? So this is how much current, the difference between how much current has to go in your control voltage into your base to get that current on your output. So what it says is you have, for 15 amps, you got to gain, doesn't show the units over here, but you have a, so the gain is 15 times to 60 times. So for 15 amps through the collector, if you put 1 amp in the base, then 15 times that will give you 15 amps. But you could have 60 times. This is where, what if you have one transistor is 15, 1 times 60? That's where those that's where the current sharing problem can come into account. Now they call this small signal current gain. Okay, this is when you're down in the low current range. Well, the gain's a little bit higher. It's 40. That's the minimum. But when you're high current, see 15 amps, it's 15. If you're trying to get 30 amps, your gain's down to 5. So that means you have to put like 6 amps into the base times 5 to get 30. So the voltage rating on the transistor, the current rating, max power, temperature, how well it gets, you know, the temperature resistance between the junction and the case, and this gain are all very important parts of the transistor. Okay, so if you haven't seen one of these transistors before, see this U? U is from top to bottom, and P is from across the width, and then D is the height here. So UPD, let's go look at those measurements. U is 38 millimeters, P is 25, so that's an inch. It's a little over an inch. And where is D? D is 8.3. So it's 25.4 millimeters per inch. Oh, sorry, here's the inch column right here. So 1.5 inch by 1 inch by about 0.3 inches tall. So they're very good sized parts.